Hey everyone, it's good to be here. It's nice that some of you are showing up. Please let me know if the sound is coming through okay. And for anyone else that's here, just who hasn't said anything in the chat, it'd be nice for you to see just to say hi and let me know who's around. We will of course get started in let's wait a couple more minutes for people to show up. Thank you. Again, thank you for bearing with us through this really extraordinary time. Hopefully, this goes okay for you guys. And as always, you can feel free to type in the chat and interrupt me throughout the lecture. There is one thing where what I do here on my end takes about 30 seconds before it shows up there on your end. So when you type a question, I'm not ignoring you really. It just takes me 30 seconds to get the response out to you. So good to see everybody. Let's get started then. With the last couple of sections, it took me about an hour and a bit to get through all the material, and I'll stick around for another 15 minutes after to answer any question. So we'll go through Ampere's law today, and then we'll also go through para, dia, and ferromagnetism, ending off with a quick word about the midterm, and then answer any questions you guys might have. So let's get started. Since most of you guys have seen the pre-lectures, hopefully, you guys have some sense what Ampere's law is about. And the motivation really is to think about that last week we did a lot of Biot-Savart law and integration, and that got a little bit heady and difficult, and all the direction get a little tedious. So is there an alternative way to do it, right? Can we look at the magnetic field distribution as a whole and say something about the entire magnetic field line diagram, similar to how Gauss's law helped us a lot in the magnetic field case. So quick reminder what Gauss's law and kind of what motivated that was, if you look at the Coulomb's law, it can be written as Q over 4 pi r square epsilon naught, right, r hat. So you have a point charge, and for a point that's r away from the point charge, you notice that there's this term here with the surface area of a sphere. So that kind of motivates us to draw these circular Gaussian surface, so we can relate the amount of we can relate the amount of electric field going through this surface, which we end up calling flux, to the amount of charge enclosed inside that volume. So can we do the same thing with magnetic field? But the funny thing about magnetic field is it always comes in these loops, right? If you have a loop of current in this case, right in the middle, it's more or less like a straight line, but most other places, the magnetic field is creating a loop. So if we draw a Gaussian surface like this, you'll see that we have 3 lines coming in and 3 lines going out. Right? If we do it here, there's 2 lines coming in and 2 lines going out, right? For other distribution, like for solenoid, if we take, say, right here, you have a whole bunch of lines going in, but you have an equal number of lines going out, right? Same thing here. In and out. Similarly, actually for even permanent magnets, it's the same thing because we tend to draw the magnetic field lines right through the inside. So if we go here, we have a bunch of ins, and we have an equal number of outs. And that's because the magnetic Even the permanent magnet always comes in a pair, right? There's a north and a south end, and so these things always form a nice, lovely loop. For a straight wire, of course, you're going to get in versus out again because these are all circular. Even if you encompass the wire itself, you will still going to get all the inward flux equal to the outward flux. Which brings us to this thing called the Gauss's law for magnetic field, or of magnetic field. If you look at the net flux, which is now defined with magnetic field, not electric field, you always get a zero. This is actually just another statement to say that there is no such thing as a magnetic monopole. Meaning you'll never find like a north magnetic pole just by itself, similar to how you would find, like, say, a negative charge just by itself, where all the electric field would just come in and terminate, so you can have a net negative flux. That doesn't happen for magnetic fields. There is no such magnetic monopole, and you get this net flux is always equal to zero. And this is a fundamental rule of our universe, and it does tell us something fundamental about the fabric of what makes up our world and our universe. However, it's not immediately useful for us to find the magnetic field at a particular point. So is there an alternate approach that we can actually make some good use out of? Well, if you look at the forms again, right, the Gauss's law is related to Coulomb's law, which has this surface area of a sphere, right? You could also argue that the Biot-Savart law also has this 4 pi r squared bit, because it's mu naught q v cross r hat. But the direction doesn't work quite as well, right? If you have a little q going in v, the magnetic field ends up being created in a circle around that. Try and draw 3D here. It's not the easiest thing. But if you do like a spherical Gaussian surface, all the magnetic field just skirts along that surface and doesn't go through. Again, net flux of zero. So instead of doing that, we look at a straight wire. So if you have a straight wire, say, coming with the current coming straight out of the page, and you're looking at a point that is r away from that wire, you know that through the right-hand rule, right? Current comes out of the page, following your fingers, you know the direction of the magnetic field, say at that point, to be upwards as it goes around and swirls around. And the magnitude of this magnetic field is equal to mu naught I over 2 pi r. So I alluded to this last week, how this is a hint, right? This is the circumference of a circular loop. So this is the hint to tell us that, oh, we can just, if we can track sort of the amount of magnetic field that goes in this loop, that will be related to the amount of current caught inside that loop. Right, and this is supposed to be pretty similar in concept anyway with Gauss's law, right? With Gauss's law, we would track the E through, right? That's a flux. A closed surface. And that flux is related to the charges in the volume enclosed by the surface. So that's kind of why we come up with a different integral, not flux, right? But a loop integral, which is the basis of Gauss's law. So Gauss's law, right? We're looking at a loop and not a closed surface. It's a closed loop, right? It's like a hula hoop in space sort of thing. And that's related to the I enclosed, with the proportionality constant being mu naught. And that's where mu naught gets defined. And so the Biot-Savart law makes use of the same constant. That's why they had the mu naught divided by 4 pi. Now, along with this whole thing comes with us, we have to consider the direction just a little more carefully. So let's look at that same situation again, right? For a wire coming straight out of the page, we have the magnetic field going counterclockwise by the right-hand rule. So then if we're interested in, say, the magnetic field at that particular point, right? If that's P and we want to find out the B at this point, at point P, we would have to draw a loop, which we call an Amperian loop, not Gaussian surface, but an Amperian loop, a closed loop that kind of follows that. But we have a choice though. Do we take this loop and walk around this loop clockwise or counterclockwise? Well, in order for the Gauss's law to equal on both sides with the correct sign, right? The direction here we have to think about a little more carefully. Say we are going to integrate counterclockwise, in which case, at this particular point, my dl would be in that direction. And since my b is parallel to dl, they have the same direction. So then we end up with a positive b dot dl, right? And so that must mean that the current, which is out of the page, must also be positive. So you can see how there's a relationship between the integration direction and the direction that we define to be a positive current. This is a little bit different than what we were doing last time with the currents and the magnetic field, right? Neither of these directly tell us what direction the magnetic field is or which direction the current is. It's by choosing the direction within which we are doing the integration, right? That only determines which direction we call positive for current. So for instance, if we take this same situation, right? And then the magnetic field again, due to the right-hand rule, goes like that. it is completely our choice to, instead of doing the integral counterclockwise, we can take the integral clockwise, in which case your dl now points in that direction. Now b and dl are in opposite direction. When we take the dot product of two things in opposite direction, you'll get a negative dot product, and it corresponds. Well, as correspondingly, we have to call a current that's sticking out of the page to be negative. Right? So the direction we call positive current changes as a result of changing the integration direction. And that brings us to yet another right-hand rule. And this is another one of these swirly ones that relate a straight thing with a curly thing, where this here is the direction of integration around the loop, and then this would be, your thumb would end up being the direction of currents that we call positive. One extra note here, the current in this case actually doesn't have to necessarily go through perpendicular to your loop. So if you look at like a hoop, right, but you look at it head on, edge on like that, so the Amperian loop, we're going to draw like that, and then say it's coming out of the page on top and into the page. So this is your direction of integration. So given that, we use our right hand, right? Fingers go out on top and in on the bottom. Our thumb is going to point to the right. And so all the right going current, all the current that goes from the left side of that loop to the right side will be called positive current, right? So this we would call a positive current, whereas this we call a negative current, but they don't have to be perpendicular. So this is, we're just going to count as a positive current, period. There's no perpendicular component or anything like that. It's just current, period, simply put. So even though this might be on a bit of an angle, we're still going to call that whole thing negative. So in practice then, you're going to see some questions that will directly only deal with this thing, which by the way, we just call this the loop integral. There's no necessary fancy name for it or even a special symbol like flux would have. But we'll give you some funky geometry, and we'll ask you for the entire loop integral. And like the Gauss's law question where we ask you about the net flux, you ignore all the electric field and all that ugly integral stuff, and all you have to worry about is finding out the currents enclosed. The one added complication here is that you have to be a little more careful about what you call positive current, right? The sign of the current will depend on the integration direction that you decide or you're given. So just check that. Otherwise, similar to Gauss's law, there are only a few select cases with sufficient symmetry that this loop integral here becomes simple enough for us to get some useful result for the magnetic field at a specific point. And let's go through those cases. First case is the infinitely long wire, right? This is the case of cylindrical symmetry. And remember, last week we got the result by finding the integral for a straight length of wire and then setting it out to infinity, so on and so forth. Quite a bit of work. So here's the problem, right? We have a wire, let's say it has an outward going current out of the page, and we want the magnetic field at this point. Similar to Gauss's law, before we use Ampere's law, we already assume that we know quite a bit about the direction of all the magnetic field, and which we do, because we have the right-hand rule. With the cylindrical symmetry, and the right-hand rule, we know that the magnetic field is going to swirl around in a counterclockwise direction for an outward going current using the right-hand rule. So to find the magnetic field at B, we would choose a Amperian loop such that every single point on there will have the same magnitude of magnetic field, which would be a circle of radius r. So on this circle, at every single point, right, your magnetic field is parallel to your dl, to your little bit of chunk of loop you're moving through. So here is the same thing, so on and so forth. And that your magnetic field is the same for all points. This lets us say that your B dot dl is simply B dl magnitudes, and then this is the same, right? So therefore, when you do Ampere's law, this guy can just come out and you're left with that, right? The magnitude of which, right? If you sum up all the magnitude of the load step we take, that's just the overall length of the loop, which would be 2 pi r as the circumference of a circle. Then we have to worry about the I enclosed, right? The I enclosed is all the current that's going through this surface enclosed by that loop. And in this case, there's only the one wire coming out straight out the middle. By the right-hand rule, right, if this is the integration direction, outgoing would be positive. So then the current here would count for positive I and not negative I. Putting this over, we get the same result as we got yesterday, or sorry, last week. And that is positive. Now, of course, this Ampere's law, like Gauss's law, only gets us the magnitude because we're supposed to know the direction ahead of time to enforce certain symmetry. So that's no big deal, right? It looks exactly the same as what we had yesterday, and so this doesn't give us anything new. Might get there a little faster, but at least it shows us that it's consistent with whatever we had before. However, using Ampere's law, it's good at giving us some extra insights as well. Just Ampere's law is really good at the things it's good at. And in this case, we can talk about specifically what happens inside a wire. What is the magnetic field inside the wire? We did outside the wire, but if you now have a wire that's kind of big and fat, right? Even though the current, it's all going out. So you can think of the current being kind of distributed throughout the wire. And I'm going to stop drawing circles. Right? You got the current coming out. But if you want not for a point outside, like there, you're looking for the magnetic field of a point inside, right there. What is the magnetic field? Well, you still have the same geometry that we expect. So if you take a Amperian loop that is also a circle, and will again go counterclockwise, of that radius, you again have all the lovely thing that we had last time where B is parallel to DL and that B is the same. So then when you do Ampere's law, you get all this stuff, and then that's just B times 2 pi r. But what is different now is that we're only enclosing part of the wire. So we're not enclosing all the wire, and therefore not all the current. So the current enclosed is actually the total current multiplied by this fraction, right? We divide by the total area and we multiply by just the enclosed area, right? That's the ratio we're talking about. And some people like to group these guys together and call J is equal to the total I over the total area. And we call this current density. And think back a couple weeks when we talked about current, we can prove that the current inside a wire is going to be distributed uniformly as well. So this current is expected to be uniform. Sorry, this current density is expected to be uniform. So coming back, we got mu naught times the I total, which is I, divided by pi. Oh, sorry. Let's call the wire to radius big R. So the total area of the wire, total cross-sectional area of the wire, is pi big R squared, whereas the area enclosed, just this chunk here, is pi little r squared. And so those kind of cancel out, and we end up with that your magnetic field is that. You can of course say that the I over pi r squared thing is equal to the current density, whatever you wish to do. The main takeaway is that your magnetic field now no longer depends on 1 over r, but rather your magnetic field shows a linear relationship with respect to r. And that's because as you go further and further out within the wire, yes, your loop length gets bigger, but the area you're encompassing grows by r squared. So that gets us a little extra insight. If you were to do this using integration, it would be quite a bit more hard work just because you're off axis and the symmetry is all broken. So you get some ugly results. You have to do some ugly expression before you get to the end. So that's cylindrical symmetry. Another symmetry, pretty common case that we like to do is the infinitely long solenoid. Last time we did a lot of hard work by integrating the little current element into a loop, right? And then we add up a bunch of loops to make a solenoid, and then we extended that to an infinitely long one to get our final result. Today, and then even if we do that, that only tells us that the magnetic field is straight and uniform along this direction, along the axis of the solenoid. But today we can use Ampere's law to kind of get to the end a little bit faster, but also to prove to you that the magnetic field is in fact uniform everywhere inside the solenoid, consider given that it's infinitely long, and not just along the center axis, but also across the area. And here's how we do it. So the first thing is we have to consider the direction of our magnetic field. And qualitatively, there's only magnetic field outside over here because the field gets out the end and back. But if this solenoid was long, then these things have no way to escape and bend back. So therefore, the assumption is that all the magnetic field inside is trapped inside. And given the cylindrical symmetry, right, the symmetry all the way across, infinitely long, that we expect the magnetic field to be parallel to the axis of my solenoid. And that these magnetic field inside cannot ever escape and loop back around because the solenoid is infinitely long. So outside, we can say that the magnetic field is 0. Now, if you want to know if the magnetic field goes left or right, the way I do it is I look at one specific wire, say this one, right, and then do the right-hand rule on it. So if it's coming out of the page like that, it's going to swirl counterclockwise. And so inside, it's going to go to the left. So therefore, everything adds up and go to the left. It's always consistent, right? Every single wire down here gives you to the left. If you pick a wire up here, right, that's into the page, so it's going to go this way, and then again going to the left on the inside of the solenoid. So to ever figure out the direction of the magnetic field inside solenoid, just look at one specific piece of wire. So then if we're ever interested, so now we're interested in the magnetic field at some point inside your solenoid. So we draw this Amperian loop. That's a little rectangular like that. This is, of course, the cut face, the cross surface face. If we cut the solenoid like that, chop it in half, right? So you see current coming out underneath and in on top. So we will have to do Ampere's law. And we have to take this loop integral. But because the loop integral has different expression piece by piece, we kind of have to do each segment sort of separately. So I'll do the easy one first. That's out here, right? Because we said that your magnetic field is 0 outside of the solenoid, then whatever integral you have with dl, you just end up with your zeros, so you end up with 0. All the section should give you 0 b dot dl. Then you have these two chunks where your magnetic field is not going to be 0 there, but you do know that it's going to be perpendicular to your dl, right? dl in this case goes that way. If they're perpendicular, your dot product, of course, gives you 0. So again, those section is going to give you 0 yet again. Then last but not least, you have this chunk in here where your dl goes in the same direction as your b. And so because they're the same radius at every single point along, you expect the magnitude of the magnetic field to also be the same, so you end up with the length of section 1, which is L. And everything else, all the other parts give you 0. And for the I enclosed, we have not just the one wire, but we have a whole bunch of wires. So that's going to be some number of wire enclosed multiplied by I. Now, direction. Since we're going to be integrating clockwise in this case, we expect inward current to be positive. So everything in here is in fact inward, so therefore positive. So the magnetic field that you have is the number enclosed divided by L times I. And this here it's exactly the same as your loop density because you're enclosing so many loops per so much length. Remember that L here has nothing to do with the length of solenoid itself, right? It's just this arbitrary length that we choose in order to draw our Amperian loop. So this, once again, brings us the exact same result as we had last week for the infinitely long solenoid. Maybe it's a little faster, but the key thing that I want to highlight is this whole derivation would be exactly the same if we make the loop this big, or this big, or this big. So the magnetic field here, and here, and here would give you the exact same result. So not only is my magnetic field the same along the solenoid axis, it's also the same across the area, which really gives us, for an infinitely long solenoid, the magnetic field inside is indeed uniform. Straight, same direction, same size. And this is something the integration couldn't have allowed us to make such statements. One more geometry I'd like to go through with you that's pretty easy is the shape of the toroid, right? In the sense, a toroid is kind of like if you take the solenoid, right, and you wrap the two ends around so that it touches each other on itself, right? If you were to visualize a toroid, you can think of a shape kind of like this. Oh wait, no, not that. It's like if you have a slinky and you take the two ends together. Right, and that's kind of the picture you're looking at. So down here, you can see that it shows you if you cut open the toroid, you can see that the cross section of each loop here, in this case, is circular. But it doesn't have to be circular, right? Each loop can have a square shape, it can have a triangular shape, it could be star shape, whatever it is, right? But as you loop it around to make the two ends join, the outside thing still looks more or less like a circle. And then we analyze all that shape the exact same way, right? We slice it right across like that. And what do we get if we do that? So if we take this toroid and slice it right across, what we see is you have a bunch of wire, in this case on the outside, giving you inward looking current, and then inside having outward looking current. So this kind of wire comes up and then goes in underneath, it comes back out, and so on and so forth. So it kind of loops like that. Then, if we're interested in, say, the magnetic field at this point somewhere inside the solenoid, that is r away from the center of the circle, then we use Ampere's law yet again. So we have to then decide the direction of the magnetic field, right? Knowing that this is pretty much a solenoid, you kind of know that the magnetic field inside the toroid should go in a circle, right? Should go along with the axis of the solenoid. The direction, again, you look at one particular point, say this one, using the right hand rule, it swirls this way, so you know that it's going to go in that direction inside, right? In this case, on that wire, it goes to the left on the inside, so therefore everything goes to the left on the inside. And by the symmetry of it, you expect that all along the circle, the magnetic field magnitude is once again the same. So if we were to draw an Amperian loop, that is again a circle, you again have the same condition where your magnetic field magnitude is the same, your B is parallel to your DL, and all that nice stuff. So then when you do the integral, you have B times 2 pi r. That, of course, is all equal to mu naught times I enclosed. The I enclosed here is you have to, in this case, it's not a fraction of the number of loops, right? You're inside, you are counting every single loop, right? For each loop, there's a wire that comes outwards on the inside of that donut. And outward looking current, because we're using a counterclockwise integration direction, outward is positive, so then we have N times I positive, right? This is the total number of loops. Which gives us the result mu naught N times I over 2 pi r, right? And in some sense, it's quite similar to the solenoid case, right? You still have mu naught I and then N divided by length, right? It's some kind of number of loops divided by the length. What is different is that B is not uniform within the toroid because it depends on 1 over r. In a sense, what they're kind of trying to say is that on the inside edge, right, your loops are more scrunched up together, higher loop density, you expect a higher magnetic field. Whereas on the outside edge, the loops are further apart, lower loop density, you expect a lower magnitude of magnetic field. So it depends on 1 over r. So why do we make things of this shape? Well, the key interesting thing comes in when we look at not just the magnetic field inside the toroid, but what if we consider a point outside the toroid, outside the circle, outside the slinky. So you can consider a point like this that's within the inside here. And if you were to do an Amperian loop, you'll find that the I enclosed here is 0. And so then your loop integral must add to 0, and by symmetry, the only possible solution is that your b is equal to 0 for all points within this region of the toroid. Similar argument goes for a point outside the outer boundary of the toroid, right? Out here, if you do a Amperian loop, you have to count all of the current that kind of goes through the surface. And so what you have is if you're going to go like that, you're going to have all these current inside going out of the page, which is your positive case, so that's your outward, plus a bunch of current that goes inside, and because we're going counterclockwise with our integration direction, the current that's inside we define as negative. So n times I minus n times I is again equal to 0. So your b is equal to 0 yet again. So that's the nice thing about a toroid, is that yes, it creates a magnetic field, but it does not create a magnetic field outside itself. In the sense, the magnetic field is contained. It doesn't leak out because it goes around in a circle and circle, circle. And this would have good benefits if we were to put this thing as part of a circuit. We don't want the thing to create magnetic field that affect other parts of our circuits. More on that in a couple of weeks. So those are the kind of geometries: the straight line wire, the infinitely long solenoid, and the toroid. Those are usually done with Ampere's law because they're easy to do, and hopefully you would agree. But there is a couple limitation of Ampere's law that, just quickly highlight. Just like Gauss's law, right? You need good symmetry in order for the line integral to give you something useful. Right? It's not that it's not true in those cases. Just like Gauss's law, it's true no matter what the geometry is. But it's just that the loop integral will not give you a magnetic field at a single point particular without the right symmetry. You'll introduce too many unknowns for you to solve for the magnetic field at a particular point. But on top of that, this doesn't apply to Gauss's law. On top of that, the current has to be steady. The current cannot be changing in time, because if that is the case, a separate physical phenomenon takes place. And we have to modify our equation to account for that. Hopefully we'll get to that by the end of the term. But definitely for this week and for the midterm, whenever we have to use Ampere's law, you can just assume that the current is in fact steady and that this condition is satisfied. Now, if you permit me another 10 minutes or so, I'd like to go through this one small topic that's dealing with the magnetism in matter, right? Well, recall that when we deal with capacitance, we had this idea where if we're not dealing with a vacuum for the permittivity of free space, we replace epsilon naught with kappa epsilon naught, so-called a dielectric constant, which in those cases, the dielectric partially polarizes and partially cancels out the electric field. So what happens if you deal with magnetism not inside free space, permeability of free space, not in vacuum, but in solid matter of some sort? Well, to no surprise, I hope, we replace mu naught with kappa mu naught. But what is actually happening? Well, inside you can look at each individual atom has a certain magnetic dipole moment, right? As that one video I show kind of went through. If you expose some external magnetic field to this solid, these little tiny magnets or tiny little dipole moment tends to line up with the magnetic field, and in fact it will add to the magnetic field. And depending on how this behavior ends up happening, we classify material into 3 general types. Paramagnetic is a fairly common type where each atom do in fact have some magnetic dipole moment, though maybe not strong, and these only align fairly weakly. So your magnetic field only ends up increasing just by a little bit. That could be due to the fact that the atoms are locked in the crystal, or they get knocked around randomly by thermal agitation. So it's hard to make the alignment, it's hard to keep the alignment. But it does help a little bit, so you still expect a kappa B of greater than 1. But usually, most material, we're talking about on the order of, say, 1.00001. So the effect is not very big in these paramagnetic material. In diamagnetic material, these are cases where the atoms in fact have no dipole moment at all. So there's no alignment happening whatsoever. So then but you would think that that would result in it basically acting as if it's a vacuum. So you expect a kappa of 1 exactly, but due to some other effect that we'll cover next week, called Faraday's law, in the absence of this alignment, you actually get to see this tiny effect that makes the magnetic field just a little bit weaker. And again, we're talking about a very small effect. It's less than 1, but we're talking about on the order of 9999. Oops. Something like that. We'll cover Faraday's law in the next chapter. Then the third case, which is probably the most interesting case, is the ferromagnetic material, where the atoms have a strong magnetic dipole moment that strongly aligns. And this alignment is so strong that once you align it, the magnetic field created by alignment can maintain itself, and that's where you get the idea of a permanent magnet. The kappa for iron, which is one of the most well-known ferromagnetic material, we're talking about on the order of 5,500. So much bigger than 1. What this means that is, since we're going to replace mu with kappa mu, if we were to say make a solenoid instead of having just in thin air, if we put a solid core of iron in it, you end up replacing mu naught with kappa mu naught. So we're getting basically 5,500 times the magnetic field for the same current. You get a much stronger electromagnet if you run the same current through a solenoid, same turn, same geometry, same everything, with an iron core inside versus without. And that's why most electromagnets you see will have an iron core. And not only does these kind of solid have the effect of strengthening the magnetic field, it also therefore has a way of channeling the magnetic field. So last day we showed you the application for like a hard drive write head, right? And you can use this concept to channel and shape your magnetic field, right? You generate the magnetic field up here in the coil, but then it gets channeled within the metal so that you choose it to only expose in wherever you want to choose. You want it to be exposed, meaning you just want it exposed within this little gap so you can write just that little tiny bit. You can do that. If you want a really strong magnetic field concentrated coming out here and more spread out back here so it doesn't rewrite your bit, you can do that, right? So you can use these metal and these ferromagnetic material to shape your magnetic field as well as strengthening it. So that pretty much cuts off the material we're covering for the midterm. Chat's been pretty quiet, so I hope you're still all there. In any case, the midterm. So the midterm will still take place next Wednesday at the same time as you would have been in class. I will send out the midterm as a PDF by email by 2:30. And if you haven't received anything by 2:40, please email me. And then you're expected to submit this midterm on Brightspace. I will put a submission folder, and you can upload whatever you end up writing. The midterm will be open book, but I do highly, highly recommend that you make some reference sheets for yourself. Just, if anything, it's good for review, and it's also good for speed, right? You don't want to be caught looking up things while you're trying to do a midterm. You want everything nice and fast and by your side. The midterm itself will be due 4 hours after I sent the email out, so that'll make it 6:30 at night. Leave yourself a little time to do any scanning and uploading. I'll send a more detailed email out about that as a reminder. The material on that midterm will include electric potential, which is way long ago, right? Think about how to relate your potential with electric field, how to find the electric potential at every single point in space, things like that. Then we had a couple easy chapters with circuits and then capacitors. And this past few weeks, we did the magnetic force and how to create a magnetic field using current, right? Last time with integration last week, and finding out how big that is with Ampere's law this week. To cap things off, before I open it up to just a general question period, a couple of you asked me on your moneyest point to kind of summarize all the right-hand rules we've done. And we have done quite a few, right? It's not just one right-hand rule, it's a whole bunch of them. So let's quickly go through that. The way I organize it for myself is I basically have one right-hand rule that does all the cross product, right? This is the 3-finger one, right? If you have A cross B, then the result A cross B would be your middle finger. So as long as I have form of the equation with the cross product, I would have, this is my thumb, middle finger, thumb, index finger gives you the middle finger. Thumb, index finger, middle finger, so on and so forth, right? The one rule for the cross product works for all cross products, and we see it in a variety of different situations. Then we have a whole variety of rules that relate something that goes in a circle with something that goes straight. For instance, if we're looking at a torque vector, then using your right hand, your finger will tell you the direction of the rotation given the direction of that vector. With a current loop, with a certain current, right, we define the magnetic dipole moment of that current loop by another right-hand rule. Given a current, the magnetic field caused by that current goes in a circle around that wire, and it's again given by the magnetic field. And today we went over one more, which is if we have a Amperian loop and we're integrating this way, right? This is the direction of integration. And then this tells us that that's the direction of positive current. So hopefully that summarize things a little bit for you and make things a little more clear. And if there's no further question, actually, are there any questions? Is anyone still out there? Well, if there's no further question in that case, then I guess I'll let you go. And feel free to contact me by email. I'll still post a quiz next Monday. We will have that midterm next Wednesday. And then next Thursday, we will be doing the same thing again. So contact me by email for anything until then. Stay safe out there. Thank you.